Hi, and welcome to another Complete 3D Concepts video tutorial. My name is Josh, and in this tutorial we'll be having a look at working with point clouds in Autodesk Inventor. Due to the workflow required to do this, I've broken this tutorial up into two parts. In the first part, we looked at how to set up your project assembly and getting your point cloud into Inventor ready to begin work, as well as manipulation of the point cloud in Inventor for easy viewing and working. In this, part 2, we will look at working with the point cloud and modelling in and around it, as well as extracting as-built information from the point cloud within Inventor. There is a link to part 1 in the description below if you haven't already seen it and would like to. As we are continuing on from the previous tutorial, we can just jump straight in. So, less talking, more CADing. Picking up with the model that we created in the last tutorial, we will start by refining our driving sketch to something that might make a little more sense for working in a room like this church hall. To do that, I'm going to uncrop the point cloud, turn off the scans I didn't need to see, and then outline the floor space with a rectangle. If we look at the point cloud in plan view, you can sort of make out the walls and doors here, but the detail is a little too hard to make out. You will also notice that if you zoom too close to the point cloud to get a better view of the detail, it turns into this unrecognisable mess of points where you can't make out any features. The reason that this happens isn't the fault of the program or the scan data though. The reason that this happens is the points are just that, an infinitely small point in 3D space. Any program that displays point cloud data adjusts the size that it displays the points at depending on the zoom level. Anyone familiar with working with PD mode and PD size functions in AutoCAD will be familiar with this concept. The issues that you're seeing here is that the programs like Inventor allow you to zoom in to a level that allows you to see the detail in fractions of a millimeter. Depending on the way that the scan data is captured and then processed, there could be as much as 25 millimeters or more between the points, which means that as you get closer to the point cloud, the program is scaling down the size of the points and the space between the points is getting greater. The result being that eventually you'll lose the detail of the point cloud that is visible at a greater view distance because of the point density on the screen and the scaling of the size of the points. If you need to see something in more detail, it may mean that you need a denser point cloud. If you already have a point cloud, getting more information added typically means redoing the entire job unless the issue is caused by the way the point cloud is being processed or if the scans are being done in a very specific way on site. Typically we work with point clouds that have been decimated to 6 millimeters as we find this strikes the best balance between software performance and the detail required for most jobs. I've spoken about point cloud decimation in the recap tutorials, so if you want to know more about that, go and check it out over there. If you are struggling to see the detail that you need in your point cloud, try and find out from your scan service provider how they process the point cloud and if it's possible to get another point cloud that has more detail. Due to this, you need to find the balance between an appropriate zoom level and a reasonable amount of detail. You will find that taking a little time to crop your point cloud to only show the detail you're interested in tracing is the best approach here. Often, a super thin slice through the point cloud is the best approach. You should take this slice at a level you intend on tying your 3D model into the point cloud as opposed to the level that your sketch is on for the best results. I'll get back to this later, but for now, we will assume that this suits us best to take a slice through the cloud at about the floor level so we can trace the walls. As you can see in the top view, it's already easier to see the detail of the walls and the general room boundaries. You can also see from this slice how bowed this floor must be, as we have clipped out the sides and a bit in the middle, but we'll get back to this later as well. To line our sketch up with the corner of the room, we will need to delete the dimensions that hold our third and fourth lines in place and drag that point back into the corner of our room. As you can see, we are missing the corner of the room here because the door was open during the scanning. But this won't be an issue as we have enough of the walls at this level that we can safely calculate the corner position by dragging the lines around and then locking it in with some dimensions. I'll now delete the lines that we drew earlier and draw a rectangle. That will allow us to get the dimensions of the floor space that we are working in. So starting here at the end point of our lines, we draw a rectangle aligned with this wall. And drag it out to roughly this wall. At this level, that looks pretty good, but if we zoom in over here and have a look, there's a little bit of misalignment. So if we zoom back a little bit and drag this line to better line up with the back wall, that looks better here. But what's happened over here? This is now way out of alignment. Right here, we are starting to see the benefits of working with point clouds. Here, you can see just how far out of square this room is and how bent the walls are. Very important design decisions can be made right here and now about how to handle this real-world issue. We haven't even modelled a 3D solid yet. How good's that? From here, you can make the decision to trace the walls exactly as they are if you need that level of detail, or you can decide that for the purpose of the job you are doing, this isn't an issue, as you have meters of clearance for what you are doing, and this bit of misalignment doesn't matter that much. But this also makes another important issue that we touched on earlier a little easier to understand. Another reason that detail is often difficult to make out in a point cloud when viewed from one angle like the top view is that what you are looking at is a feature that is not straight or perfectly vertical or horizontal, like this wall. Who would have guessed that of a 130-plus-year-old church, huh? Aside from being bent and out of square at this level, in this direction, it is also bent and out of square in the vertical plane. So when viewed like this from the top view, what you are seeing is the points that make up that whole wall from top to bottom, and this is the very confusing result. This is also why it's best to take a slice through the point cloud at a level you'll be working at. If you take your slice through at the bottom of the wall, and the top of the wall is 10 to 15 millimeters off vertical, that means that you will either need to adjust your model again later, or your new model will be 10 to 15 millimeters wrong. To most people, 10 to 15 millimeters might not sound like that much, but let's put that into the perspective of a plant model where we might be adding steelwork or a pipe or something between these walls. If they are both 15 millimeters out of square towards each other, that's a total difference of 30 millimeters or 3 centimeters, or for our imperial using brethren, a little under 1.25 inches. If this issue wasn't picked up until the day of the installation, then it could potentially cost tens of thousands of dollars in reworks and delayed deadlines. Here, we are highlighting the issue long before a drawing is even started, let alone a bit of steel being cut or a crew being left standing around on site while steelwork is being modified. We'll get back to how to work out how much this is out by in a little bit, but for now, we will work on the assumption that it is more important for us to be aligned with the back wall and inside the existing walls, so we will adjust our rectangle to suit and lock it in place with some dimensions. As we deleted the lines we made in the first tutorial that we constrained our original planes to, we will need to redefine those planes. From there, we will also need to fix any mate issues as a result of these changes. And now we should be good to go again. Now that we have a driving sketch that more closely represents our room with the origin that makes more sense for our project, I would typically dive straight into concept development. All the as-built information is here in our point cloud that I can model around and measure to, so there's no need to extract any 3D information at this stage. So let's have a look at how we might do that. In our all other parts assembly, we know that the origin point is at the top of the floor and the inside corner of our room, or close enough in this case. We also know the size of the area that we're going to work in due to drawing a rectangle in the driving sketch instead of two random length lines. And we know that we are parallel with the wall that matters to us. For this project, we were tasked with placing some bench seats in the hall for some visual representations for use by the church. In order to do that, we need to create some geometry to constrain to. So we'll create another driving sketch for our all other parts assembly and create that geometry in there. Once we have our new driving sketch part in place, we can come back to our main model, and in the same way we did our main driving sketch, we can create a rectangle starting at our origin point, and using a point cloud as a reference, we can estimate the location of our first bench seat. From there, we can create the planes that we will need to constrain to, and then we are ready to place our bench seat, or any other piece of equipment in this position. To keep things simple, this sketch and planes could also be done in the main assembly driving sketch. There are pros and cons to doing that, but I find which way I do it depends on the job that I'm doing and what I want to do with the model later on. As this is a small and simple job, this is all we need to do here now. But if we were doing a larger, more complex model, you could continue to flesh this driving sketch part out with all the grid sketches and equipment locations required for your job. In order to place our bench seat, we'll have to remodel it off the point cloud. So let's have a look at how we extract our 3D information from the point cloud. Back in our point cloud part, I can uncrop the point cloud, and using the navigator, I can now turn the bench seat back on so that we can work with it. Due to the way I want to work with this bench seat model downstream, I want to make a part to do the 3D solids in and have the origin of that part centered in the seat at the ground level. To do this, I will need to create some more geometry in the main driving sketch to constrain my bench seat part in. I do this using the same methods as we used to create the first sketch. Now that I have a part constrained in the correct place with the origin I want, I will create a plane in this part offset to the height of the seat and then sketch on that plane a rectangle the size of the seat. I simply extrude that to the correct thickness by aligning the point cloud correctly and then dragging the grip to the right place. When doing this, it pays to keep some standard dimensions in mind for things. In this case, I know the standard thickness for a dressed board is about 25mm, so I know that this extrusion is within a millimetre or so of the correct thickness despite having not taken a single manual measurement while on site. I can then offset a plane from the origin of the model for the legs and repeat the process to model the rest of the details. This process is the same regardless of what it is that you're modelling. Some things are harder than others to remodel obviously, but this is all there is to it. Offsetting planes and drawing sketches. Seems awfully familiar, doesn't it? The only difference between your normal workflow is that you don't have to think real hard about the dimensions for this because you are using the point cloud as a guide for the sizes. There are other programs that will allow you to do this modelling process in a more automated sort of fashion, where the program first calculates the profile of the point cloud and then using an average of the points for that profile, it will create a plane or a shape for the best fit. You can read all about why I don't like to use these programs in an article on our website that I've added a link to in the description. The crux of the article and why I don't like that workflow for even small things like this seat is highlighted at the start of this video tutorial by how far out the walls are for the main hall. While it is obvious to us that the wall is bent, the algorithms that these programs use do one of two things in this situation. They will either only do a patch of the wall or a part of the wall that is flat enough that it fits into the limit of the algorithm, or if all of the points on the wall fit into those limits, then it will do a flat patch where there is a bent wall. Neither of these results is a particularly good one, and both are a long way from the desired or ideal. When you consider that solids creating using this method can be very difficult to use in drawings, it really isn't a great way to work. Modelling things directly within Inventor puts the power in your hands on how best to handle this issue. Also, the 3D models that were created within Inventor will be easier to use in drawings. That said, like any tool, there is a use for working this way, and it's either something that you need to experiment with in your own workflows to see if it works for you, or consult your scan service provider to see if there's a cost-effective way to do this for your job. Now that we have our part modelled, we can place it into the All Other Parts assembly and mate it to the geometry that we created earlier. Checking the placement back in the main assembly, we can see that our floor plane isn't quite at the right height for the placement of this seat. So I can crop the point cloud in order to see the floor area better using the techniques shown in the last tutorial, and adjust the floor level to suit. As you can see here, there's a pretty big bow in the floor, so we'll need to work out how much of a bow and if that's going to be an issue. So we move the floor plane up so that one leg is on the floor proper, and measure the difference from the base of the foot to the point cloud. Here, you can see that it's only about 40mm of deflection in the floor. For what this is, I don't think that'll make a huge difference over the length of this seat. So we can leave it at that. Of course, for a plant model, or something where the stakes are a lot higher, this is an issue that can be discussed and a decision made now, rather than when there's a crew of people standing around on installation day. From here, we can pattern the part out to see what the hall would look like filled with seats. To check if our spacing is right, we simply use this measure tool as we normally would and select a face on the seat and then click on the point cloud. From there, we can adjust the dimensions accordingly to center and space the rows of seats. It's really that easy. And that brings us to the end of this tutorial. If you have any questions, please feel free to post in the comments below and I will get to them as fast as I can. Otherwise, if you think we can help you with your scanning or Inventor needs, please feel free to get in touch. In the future, I will be doing videos on how to work with point clouds in different software and some more in-depth tutorials on workflows. I will also do some tips and tricks tutorials as well, so if you like what you've seen here, don't forget to click the like button below and be sure to subscribe so you can get updates when the new videos are out. Thanks for watching and catch you next time.